Hello and welcome to this really quick video where we're going to be looking at just the basics of circular motion. So the first thing I'm going to do is look at, I'm going to remind you about radians and look at angular displacement before we go on and look at some of the sort of newer aspects of circular motion. So here we've got something moving in a circle. Let's imagine it starts at A and it's moving round on this circle to B. The radius of the circle it's moving in is R and it moves through this angle theta here. Now we can define the angular displacement, basically the angle it moves through like this. S is just the arc length, so that's the arc length, which is just the distance from here to here, so that's measured in meters, like that. This is R is our radius of our circle, and so that's also measured in meters, so that's that there. And if we do that divided by that, it tells us the angle that this thing's moved through in radians. So that's measured in radians. So we can do little things like this. We can show the number of radians in a complete circle is this by using this equation. So we have theta equals S over R. For a full circle, going all the way around, the arc length is just the circumference of the circle. The circumference of a circle is 2 pi times the radius divided by the radius. So these two radii cancel out, and so we end up with theta being equal to 2 pi. So that's one way to prove that the angles in radians in a circle is 2 pi. So what we're going to look at now is we're going to look at something called angular speed. In the same way that normal linear speed is basically the rate of change of distance, it's just distance divided by time, the angular speed is basically the same thing, it's the angle divided by the time. So this is our angle again, so theta is our angle, measured in radians. Time is, t is time, sorry, which is measured in seconds, and then this symbol here is at omega. A lot of people say it's a W, it's not, it's a Greek letter omega, and this thing is the angular speed and it's measured in radians per second, so we would write that as radians per second like that. So let's do a little example. So we've got an old record player. It rotates at 33 RPM. I want to find the angular speed of this record. So the first thing I need to do is know what this is. RPM basically means revolutions per minute. In other words, it's how many times it goes round once. So how many times it goes round per minute. So this thing is going around 33 times every minute. So we can work out the number of radians it does every minute because it does 33 revolutions. Every revolution is 2 pi radians. So that, if we worked out what that is, that would give us the number of radians it does in one particular minute. But angular speed is not radians per minute, it's radians per second. So I need to convert this into seconds. So to do that, I do the number of radians, and this is the number per minute, so per second would be that. And so therefore, if I just do that on my calculator, I end up with this. So I get that the angular speed is 3.5 radians per second. So every second, the thing's moving through 3.5 radians. So that's how you work out the angular speed. It's often good to know, if you know the angular speed, to work out what the linear speed is. In other words, if we know what the angular speed of an object here is, we can work out how fast the thing's actually moving in terms of meters and seconds. To do that, if we take this is our definition of speed or velocity from before. So this was our speed in meters per second. This was our distance or displacement in meters, and this was our time in seconds. We can use the equation we've just had a look at. So the angle is the arc length over the radius. The arc length is the distance this thing's traveling, so we can rearrange this to get the distance equals r theta, like that. If we take that and put it into here, we get v equals s, which is r theta, divided by t. Okay, so we've done that. It's still not given us a link yet between the linear speed and the angular speed, because the angular speed is not in here, but we do know that the angular speed is theta over t. Now I've got a theta in here, so I could basically say that theta is equal to omega t, like that, and I could substitute that into here. So the velocity equals the radius times by theta, which is omega t, divided by t. So I've got t on the top and t on the bottom, they cancel out. So I end up with the velocity, the linear velocity equals the radius times the angular speed. So this is our linear one, that's our linear velocity, and this one here is our angular speed or angular velocity, and this is just the radius. As for what they're measured in, this is measured in meters per second, this thing is measured in radians per second, and this thing here is just measured in meters. So if I know two of these, I can work out the third one. So let's go back to our record again. It's still rotating at 33 RPM. I want to find the linear speed of the edge of the record, and the diameter of the record is now 40 centimeters. So I've been given a bit more information. So if I take the equation that I've got, velocity equals r omega, linear speed equals radius times the angular speed. I know from our previous calculation that omega is equal to 3.5 radians per second, like that. So I'd basically just take the extra information I've got in here. So velocity equals the radius. Now I've got to be a bit careful because it's giving me the diameter, but it's giving me in centimeters. So obviously the radius is half the diameter, so it'll be 20 centimeters, but I need it in meters, so that'll be 0.2 meters times by the angular speed. So if I do that, I get 0.2 times 3.5, so I just get 0.7 meters per second, like that. So the edge of the record is travelling round at 0.7 meters per second. Now the final thing we often want to look at is the frequency of this thing, because this is a little bit like an oscillation. Because if you remember back to Unit 2 and oscillations, the oscillations we looked at basically repeated themselves, so which is exactly what this does, because it goes round in a circle, and once it gets back down to here, it's repeating itself. So we could associate a frequency with this. So we could say that the frequency of this motion is so many hertz. So to do that, what we do is we start off with this equation again. So the angular speed is the angle divided by the time, and we think about what happens for a full circle, because if we can work out what goes on for a full circle, we can then link that to the time period, and then and then link that to the frequency. So for a full circle, we know that the angle it travels through is 2 pi, because there are 2 pi radians in a full circle, and the time will be equal to capital T, and this is the time period. So you remember back to Unit 2, the time period is the amount of time it takes to do one oscillation. In other words, it's the amount of time it takes to do one circle. So if I substitute those into here, I get omega equals 2 pi over t. Now, very often that's a useful equation in itself, because you'd want to know the time period of this. In other words, you want to know how long it takes to do one revolution. We want to go one step further and think about the frequency. Now, the frequency equals 1 over the time period. So if we take this, we write it a bit funny. So 2 pi times 1 over t. 1 over t is the frequency, so we end up with omega equals 2 pi f. So we just tidy that up a bit. Omega equals 2 pi f. Omega is measured in radians per second. 2 is just a number, pi is just a number, frequency is measured in hertz. So provided we know one of those, we can work out the other one. So finally, let's go back to our record. It's still rotating at the same speed. I want the frequency of this motion, so I just do the same thing again. I write down my equation that I've just looked at. So omega equals 2 pi f. So I can rearrange this. F equals omega over 2 pi, because I'm actually wanting the frequency. I know that omega is 3.5 because I worked that out right at the beginning. So I just put that into my equation, and I end up with 0.55 hertz. So my frequency is just 0.55 hertz. So again, there are a few things that I've been able to calculate just basically from first principles. So as a really quick summary, we looked at the angular displacement, which is measured in radians, and if you want to work that out, it's the arc length divided by the radius. We then looked at the angular speed, which is measured in radians per second. The angular speed is this symbol omega here, and to work that out, you take the angular displacement in radians, you divide it by the time in seconds. We can link the angular speed with a linear speed, which is measured in meters per second, given by this equation here, where r is the radius in meters and omega is the angular speed in radians per second. And finally, if we want to associate a frequency with this thing, then the frequency is simply given by the angular speed equals 2 pi times frequency. So if we want to work out the frequency, we can simply just rearrange that equation. So that was a very quick summary of the basics of circular motion. I hope to see you again soon.